So thank you a lot, Ron and Barbara, for accepting the invitation of speaking here. It's a second webinar of One World Probability Seminar for this fall semester. And yeah, let me say it's a pleasure to have you both here. And it's a joint talk on minimal surfaces in a random environment. And we start with Ron and then Barbara. So Ron, please, the floor is yours.
Okay, thank you very much. So it's a great opportunity to speak here in the One World Probability Seminar. Thank you for the invitation. I'll speak about minimal surfaces in a random environment, which is a joint work with Barbara, speaking with me, and also based on some other works with so this work with Barbara is with Dor and Daniel, and there will also be other works with Michal Bessan and Shoni Gilboam and Michal Bessan and Paul Dario. So minimal surfaces in a random environment. So I just draw a picture. It will all be explained in the next slides, but you see here there is a path. This path is supposed to be a one-dimensional surface. One-dimensional surface is a path in a two-dimensional space, whereas this path is supposed to illustrate a one-dimensional surface in a three-dimensional space. And here we see something a bit different. We see an actual surface. This is supposed to illustrate a two-dimensional surface in a three-dimensional space. So we will have all these options. D is going to be the dimension of the path, little d, and n is going to be the codimension. We'll see that later on. So let's start. So what are minimal surfaces? A minimal surface is a surface that locally minimizes its surface area subject to boundary conditions. So here is a picture. This is a natural phenomenon, as you can see, with soap bubbles. So we have a certain boundary conditions given by this metal wireframe, and then the surface interpolates the boundary conditions, trying to locally minimize its surface area. This natural phenomena investigated in several areas of mathematics with practical applications, as you can see. So our question is, how would a minimal surface in a random environment look like? Of course, we have to explain what does that mean, but the idea would be that the area measure is not the standard one, but somehow perturbed with local random perturbations. So what seems to have the minimal area might no longer have, because maybe these perturbations made it a bit larger than we thought it was. So let's now go to try and explain some models in which we can realize this vision of a minimal surface in a random environment. And the first model that I will talk about is actually for minimal pads in a random environment. It's a very familiar model, first passage percolation. Perhaps some or many in the audience have seen it before. Then this would be to some extent review, and we will have some new results as well. So what is a first passage percolation? Let's go directly to the picture. So we have the lattice, in this case, the square lattice. So ZD, capital D, and here capital D is 2, the square lattice. And every edge of the square lattice has a number associated to it. These numbers are non-negative, and they are random. They are independent and identically distributed. I call them the edge weights. So this edge has the weight 4, and this edge has the weight 8.3, and so on. These numbers you should think about as the time it takes to traverse an edge. So to traverse this edge with 9.2, it takes 9.2, say, seconds to traverse. And now you're trying to find the shortest time to go from a point U to a point V. So you're looking at all the ways, all the paths that connect U to V, and you're summing up the time that it goes to pass through an edge, and you're trying to find the path of minimal time. So this is called the passage time. It's the minimum over all the paths of the sum of the weights on the edges on the path. This is obviously a minimizing problem. So it corresponds to minimal paths, as we saw, in a random environment. This is the environment. Let us find the minimal path in this picture. Here it is. This turns out to be the minimal path in this picture. We can see that if all the edges had passage time unity, just one, then the minimal path would be a straight line. If v was at an angle, then there would be many minimal paths, but being on the same axis as u, it would have been a straight line. Here you see it's not exactly a straight line due to the randomness in the environment. So this is a model where we can see a one-dimensional minimal surface in a capital D-dimensional space. I've only plotted here the two-dimensional case. You can also do it in 3 or higher dimensions. And again, let's continue with this. So what is known about this model? The goal is to understand the large-scale properties of this metric t, the time that it takes to go from u to v. It's a random metric. And in particular, understand how a long geodesic or a long minimal path looks like, and what is its passage time? What is the time itself, the geometry and the length or passage time? Here you see it done in 2 dimensions. So the dimension is 1 and the codimension n is also 1. Here you see it done in 3 dimensions. So the dimension is 1 and the codimension n is 2. Here we see illustrated another phenomena one might look at. Instead of studying only a single geodesic from a point to another point, we take 2 geodesics, or in this case, many geodesics from the point to any of the points here, and we see some interesting interaction of geodesics. The geodesics go together for a while and then split. So this is the phenomenon of coalescence. We talk about it a bit later. So our goal is to understand geometry and length. What is known about these 2 questions? So we speak of the roughness and the length exponents. How far is the geodesic from a straight line? A straight line is what you'll get if you had no randomness. This problem is supposed to be in the Carter-Parisi-Zhang KPZ universality. What the physicists tell us is that if you plot the geodesic and the distance from its endpoints is L, then the deviation from the straight line, the vertical height, or if you're in higher dimensions, the height in any of the other directions, should scale like L to a power called psi. Psi d, and psi depends only on the dimension, does not depend on the direction in which you're heading. The same in all directions. This is predicted. It is not actually proved. It is believed that in 2 dimensions, this psi is 2/3. So perhaps you had the intuition that this path looks a bit like a random walk or a Brownian motion. This intuition would not be exactly correct because this path, in the deviations from a straight line, it goes to L to the 2/3, whereas a random walk or Brownian motion goes to L to the 1/2. So it's super diffusive, more than a random walk. This is only in 2 dimensions. It is believed that the exponent decreases, non-increasing with dimension, and that it's always above 1/2, above the diffusive behavior. But it is open, even in the physics literature, they debate, the simulations are inconclusive. Does this exponent ever become 1/2? This is a very interesting open question, even in physics. So this is about predictions. This is about physics, if you will. What is known rigorously in mathematics? Well, and the results are very poor. We know that the geodesic is not a straight line. We know that this psi d exponent is positive. Even a bit better, we know it's at least 1 over the ambient dimension plus 1. So in 2 dimensions, we know it's at least 1/3. We expect it to be 2/3, but we only have 1/3 as a lower bound. At least we have some lower bound, at least it's positive. From the other direction, as an upper bound, we have nothing, which is amazing. This is open since the initial paper of Hammersley and Welsh from 65. So it's more than 60 years now. We have 0 from the other side. There's a trivial bound. Psi d is at most 1 because I assume the edge weights were bounded. So it can never be more than 1, bounded also from 0. But there is no other upper bound on it. This is a very, very important question related to the strict convexity of the limit shape. Other phenomena, we spoke about this phenomenon of coalescence of geodesics. Has been progress on that. There are non-quantitative coalescence results, first by Dameron and Hansen conditionally, then by Alberg and Hoffman unconditionally, only in dimension 2. And there are conditional results. In this model, people sometimes prove conditional results. If you know the following, then the following is true. Very strong but conditional results are known in all dimensions by Ken Alexander. Recently, in work with Barbara and Dor Elboim, we showed that there is even quantitative coalescence, that there is a certain power, at least 1/8, that if the endpoints and the starting points of two geodesics are within L to the 1/8 from each other, they will coalesce. So we managed to solve a quantitative coalescence problem. This also solved the problem of Binyamini, Kalai, and Schramm, a midpoint problem, maybe mentioned by Kesten even. And we have a variant of this, but not exactly that, for all dimensions, but the quantitative coalescence as is in 2 dimensions, a variant of the midpoint problem. So this is about the deviation from a straight line. What do we know about the passage time, the time it takes to go from one point to another? Okay, so it is believed the focus is on the second order behavior. The expected time to go from one point to the other is known to behave linearly in the distance. The constant in front of the linear behavior is not known. This is again the limit shape. But the focus for me is on the second order behavior. What is the correction to linear behavior? We'll measure it in terms of the standard deviations. Again, the physicists tell us that the standard deviation of the passage time should have an associated exponent chi d. The time to go from a point to a point is linear in the distance plus minus a power of the distance. The power is called chi depending only on the dimension, not the direction. And this power is believed to be related to the previous power, the height fluctuation exponent, by the scaling relation chi d is twice psi d, the deviation exponent, minus 1, the height deviation exponent, minus 1. In particular, in 2 dimensions, because psi was predicted to be 2/3, this should be 1/3. But what is known mathematically? Again, very little. We at least know that there is a upper bound of square root L. That's not that hard, but we at least know an improvement to that. You can have L over log L. This is a very nice paper of Binyamini, Kalai, and Schramm using influences of random variables and later extended by several authors. That's from above. It's still not L to the 1/3 or anything like that, but at least it's something. From below, we only have a lower bound in 2 dimensions. This relates to the previous question because we see this scaling relation. It was unknown whether psi is ever 1/2. If it is 1/2, then chi would be 0. So then a non-trivial lower bound might not be possible in higher dimensions. We don't know. But all we have is in 2 dimensions. And again, it's a rather poor bound. What about the scaling relation itself? It has only been established conditionally for this model. Recently, for a somewhat different model of rotationally invariant first passage percolation, it has been established unconditionally by Alan Sly, Reedy, Basu. But it is in that model, which is itself a bit different, and they still have to verify assumptions that they know how to verify, but are not yet done. Okay. If you want to know more about first passage percolation, I refer you to the excellent book by Uffinger, Dameron, and Hansen, 50 Years of First Passage Percolation. But I hope that I've illustrated to you that many of the very basic questions on this model remain open. We do have detailed understanding sometimes, not for this model, for a different model, so-called directed last passage percolation with specific edge weight distribution. only in 2 dimensions, but then we do have, in fact, detailed understanding. We know the scaling limit, the directed landscape of Ortmann, the Auvergne-Ortmann and Virag. But there is no such model known for first passage. It's just believed to behave similarly. Okay, so we've spoken about first passage percolation, which is a minimal path in a random environment, but we would like to get to minimal surfaces in a random environment. So now we would like to have some kind of surface. Can you have a model like that? Let me explain how to modify the previous model to be of that kind. In first passage percolation, we gave each edge a number, these edge weights, and then we found the path of shortest passage time between 2 points. Now, what we're going to do, we're going to rotate the edges. So let me zoom in. You see, this edge was 8.3. Now we rotate it 90 degrees, and it's 8.3, but it's vertical. We took this edge, it was 4. We rotate it 90 degrees. There, it's 4 horizontal. That's what we do to all edges. Of course, I didn't change anything. I just rotated edges. Now, the question we're going to look at, we phrase it a bit differently. It's the same thing, but we phrase it a bit differently. So I used to, there was a way to exit this. Oh, there we go. So we phrase the question differently. Now we think that these points in light blue over here, these cyan points, do you say? And so now there's no more a way to zoom. I don't know why. It worked once, which is nice. Okay. Anyway, so so you see these cyan points, and you see these orange points. So now what we're doing, we're looking for a way, we're looking to cut, take your scissors and cut certain edges in a way that there will no longer be any path from a cyan point to an orange point. You have cut all the ways to reach from here to here. And you're looking to cut the edges which have the minimal weight. This is the idea here. The edges that the sum of the weights of edges you cut is minimal. If you take this point of view, then your geodesic becomes the minimal cut in the dual network. But it is the same thing. It is because we wrote it is exactly the same thing. I just take a different point of view. It's not the shortest path between 2 points. It's the minimal cut in a dual network. But nicely enough, this point of view generalizes to higher dimensions to create surfaces. Now, if we consider the same model in higher dimensions, so we take a cube, and the upper half of the boundary of the cube is these cyan points, and the lower half of the boundary of the cube is these orange points, then we're looking to cut little plaquettes between squares like that, so that there is no more a path from the top to the bottom, a path from cyan to orange. And we're looking to find the plaquettes whose sum of weights is minimal, where each plaquette carries a weight. Each plaquette is dual to an edge, and the edges carry weights. So this is a minimal surface in a random environment. It's the surface that cuts away the upper half of the boundary from the lower half of the boundary of the minimal weight. In this way, we indeed find a model for a minimal surface. Let me also mention another point of view on the same model, maybe giving it even more interest. And here, okay, just to recall our notation, this is a 2-dimensional surface in a 3-dimensional space. So little d is 2 and little n is 1. This kind of minimal surface admits an equivalent statistical mechanics description. Recall again that each edge carries a weight. This is the same weight as the dual plaquette. So plaquettes are like rotations of edges in 3 dimensions. We should think that what we have is an Ising model. Here, these cyan points, they correspond to pluses. The orange points correspond to minuses. we're looking to fill the box with pluses and minuses in a way that minimizes the Hamiltonian sigma u, sigma v, where the coefficient, the coupling constant, is the edge weight tau. The minimal way to fill the model creates a domain wall between pluses and minuses, and this domain wall is exactly the minimal surface. So what we explained earlier to be the minimal cut in a network is the same as the ground state of a random bond Ising model. It's just another point of view. If you like it, great. If you don't, you can think of the other one, but it serves to motivate further. Now that we've introduced the model, we can ask what is known. And again, we can ask what do we even want to know? A basic question could be, as before, how far is the minimal surface from a plane? If you put boundary conditions which are planar like that, how far is it from a plane? This would be this H. What is known about this question? Basic change. How flat is the minimal surface? Does its maximum, say, reach a power of L, a power of logarithm of L? Is it localized? Is it order 1? Again, you might have in mind other surfaces you may have seen. For instance, say the Gaussian free field is something very familiar to people. The Gaussian free field doesn't reach very high in 2 dimensions. For a 2-dimensional surface, only reaches like square root log L. Will we have square root log L here? In the Gaussian free field is localized for a 3-dimensional surface. Will this be localized? Will it be order 1 at a typical point? Well, again, we take our edge weights, the weights attached to a plaquette or the dual edge, to be uniform on an interval AB and independent. We have the following results. This is joint with Michal Bessan and Paul Dario. We know that a 2-dimensional surface, a 2-dimensional minimal surface in a random environment delocalizes. E.g., the expected highest sign change, so the highest plaquette above a uniformly chosen vertex, is at least square root log L. Is not a very good lower bound, not a very good delocalization lower bound, but at least we know it's not flat. It does delocalize. So it is progress. We actually expect this to be a power of L in 2 dimensions for a 2-dimensional surface. So we are 3 or more orders of magnitude away, but it's better than nothing. What happens in higher dimensions where the Gaussian free field is localized for a 3-dimensional surface? With Michal Bessan and Shoni Gilboa, we have proved an interesting thing. The surface sometimes localizes, but this we have proved it only under the assumption that this weight distribution is close to a constant. For instance, if it's uniform from 1 to 1.01. So if all the weights are almost the same, all the weights assigned to a plaquette are almost 1 up to 1.01, no more than that, say. Then we know that the surface is flat in 3 dimensions. If you take a uniform vertex, even any vertex inside, then the height is order 1. Is this condition necessary? What is expected? What is expected on the surface? And let me mention before that analogous results to us were proved earlier by Bovie and Kulske, but not for this model, for the so-called disordered solid-on-solid model, which is an approximation of this model, but it's easier because it disallows overhangs. I'll go back to overhangs later, but they are actually a significant issue here. So these are the results. But what is predicted? What do we believe? In fact, the predictions still leave a lot to be desired. We believe that in 3 dimensions, for a 3-dimensional surface, this condition is necessary. That is, if the weight distribution is not a perturbation of a constant, if it's, say, uniform between 1 and 100, then the surface no longer localizes, should suddenly delocalize. We even believe it delocalizes like a power of L, very strongly delocalizes. So we believe that there is a roughening transition, surface becomes rough, as you make the disorder more spread in the disorder strength, we say, in dimension 3. But in dimensions 5 and higher, we believe that the surface always localizes. You do not need any condition on A and B. We're unable to prove any of these things, especially this conjecture, the roughening transition. I find it fascinating, but we are unable to prove. So again, this model leaves a lot to be desired. But at least we have something, delocalization in 2 dimensions and localization in 3 under a condition, even if not with the best bounds. Dimension 4 is less clear. We think it might localize for all AB, but this is a more marginal, it's a critical case. Okay.
Ron,
Yeah, Federico.
maybe let me just ask very quick, but do you expect also, do you have some guess from numerical simulations at least what the transition should be in dimension 3? And
You mean
which
the
type?
value of B minus A over A? Is that what you're saying?
Yeah, yeah. And also
I've
like the
not
size of the localization.
the height of the height of the minimal surface when it is delocalized, you mean?
I mean
Or,
both. So if you
okay.
have a guess, like I don't know, it's 1 the transition, this transition.
So I don't know what should be the value of this ratio that will induce delocalization, but the physics literature does give me some predictions on how high it will delocalize. When B minus A over A is small, then it localizes. Then when it reaches a critical point, the physicists say it will go to height square root log L. And when you go above the critical point, it should go to L to a power. Much, much stronger delocalization. I will comment on the power later. So
Okay.
these are the more detailed predictions that one has.
Thanks.
Okay? Sure. Okay, so I've told you about minimal pads in a random environment, first passage percolation, and I've also told you about a model for minimal surfaces in a random environment, this either minimal cut or random bond Ising model, domain walls, as you prefer. But in all of these cases, the results are very far from the predictions. Can we do better, maybe for a different model? This is the main topic of today's talk that Barbara will talk much more than me about. We introduce a new model, somewhat new, I will comment, was known before, harmonic minimal surfaces in a random environment. That's how we call it. The idea is that this model is more amenable to analysis, but it still models the phenomena we care about. So we want to know what is a minimal surface in a random environment. This is supposed to model a little d dimensional surface in a capital D dimensional space. The codimension, we call it n. As we will see, it minimizes the sum of an elastic energy and an environment potential energy. This is the random environment, subject to given boundary conditions. So what is this model, the harmonic model, harmonic minimal surfaces? I have the next slide explains it better, so I don't dwell on the definition yet. But let me just say we have a definition, and again, the goal is to study the geometry and the energy or this quantity of the minimal surface on large domains. Let's move to the next slide to explain this model. So again, this is the model. Let us see a picture first. So here we see the previous model. The previous model was this minimal path, or it could have been also the plaquettes, so it could have been a minimal surface. What are some features of this model? It has integer heights. That is, whenever you go to the right here, you're always going at an integer height. You're following a lattice, you're on a lattice. That's one feature. Another feature that this model has, it has overhangs. What do I mean by an overhang? I mean that there is some lines, in this case, for instance, this line, which cross vertical lines. I mean, there are some vertical lines which cross the interface multiple times. This is what I mean by an overhang. Okay, on the On the contrary, in the new model, so this was the old model, and in the new model, I will have something a bit different. I will have a model where the heights, it's still, the base is still discrete. There's still a lattice on the bottom here. So here it's just the integer, that's just one dimension. But the height is not integer, it's real. The heights are real. More generally, if you want codimension 2 or 3, you take the heights in Rn. So you put a plane at each vertex. That is also possible. So you see, that's one difference. The heights are real. Another difference is that overhangs are not allowed. So this is like a directed model. For first passage percolation, you'd say it's directed, because for any vertical line, it only intersects this path once. So that means it's really a function. You just have to choose at what is the height above every base vertex. So the surface that we call phi is simply a function from zd to Rn, continuous rather than integer valued. Okay? This is the first thing about this surface. What more? We have this energy. To a given surface, we associate an energy and want to minimize the energy. What are the different parts of the energy? Let's focus on the first one. The first part here, what it says is that when the surface changes heights between adjacent vertices, it pays a quadratic penalty for doing so. You change your height by 7, you're going to pay 49. It's allowed, you can change by any amount you want, but you pay quadratically. This is again a bit different from here. Here, when you went up, you paid the number on the line, and the numbers of the line were order 1. So you paid 1. If you went up 2 steps, you paid the sum of the two numbers, but that's like paying 2. If you went up by 100 steps, roughly 100. So here, the cost to change height is linear. Here, it is quadratic. But in fact, it will make it easier. We will see. So it's everything about this model is special. So if you change it a little bit, it's no longer a nice model as it was. It's very important to do it this way. Okay, and now we arrive at the last part. The last part is where the randomness comes in. You see there are these random numbers on edges. We have to put randomness here too. What we're going to do, we want to put randomness on the points of the real line. Let us look at that. On each real line like that, we have some function. This function we call eta. There is a different function for every copy of the real line at every position. And this function just tells us what is the cost if you pass here. If you pass here, the energy for you to pay is the value of this purple function at this height. If you pass here, then it's the value of this purple function at that height. If you happened to pass here, the value would be very high. So this is an unfavorable position to pass. But this is a pretty favorable position because the value is low. What you want to minimize is this quadratic cost of changing plus the values of the purple functions that you pass through. You're minimizing a sum of an elastic energy which tries to make you flat and an environment potential energy which tells you what is the cost of passing through the position that you go through. These purple functions should be thought of as like these random numbers that were on the edges. So mostly the horizontal edges, I would say. So it's like if you want to go through a certain, in this case it's rotated, so the vertical edges. You want to cut through a certain vertical edge, this is the price you pay for that edge. So you're trying to find the minimal way, minimizing this energy, this Hamiltonian. All of that subject to boundary conditions, to where you start and where you end. This is the model of harmonic minimal surfaces in a random environment. What remains to be specified is the distribution of the disorder eta. That will be done later. But for any eta, this is the model with quench disorder. Here the picture is for d equal 1 and n equal 1 because that's easier to draw. So this is a one-dimensional surface in a two-dimensional space. But it's also interesting to consider a two-dimensional surface in a three-dimensional space. It's harder to draw. Again, there is a lattice on the bottom. and at every vertex of the lattice, you choose the height. And in this way, you create a surface. So altogether, phi is from ZD to Rn. This is supposed to illustrate a picture for D equal 2 and N equal 1. All right, so it's important to get an idea of the model. If something was unclear, you're welcome to ask me questions. Okay.
From the audience, doesn't seem so. So it's kind of a polymer.
It's kind of what?
It's kind of a polymer random environment. This with this gradient cost with this quadratic penalty.
Yes, so for people who know, this is like a Gaussian free field energy, but we added to it some environment energy as well. And we're trying to minimize, so it's at 0 temperature. Maybe that helps.
Mm-hmm. Okay.
Okay, so now why have I introduced this model? It's more complicated than before. The reason is that we can say more about it. And this is what I would like to go into now, but I'll say something about the background. So we want to say that we are the first to study is not exactly correct. In dimension 1, d equal n equal 1 mostly, but altogether just in d equal 1, Yuri Bakhtin and collaborators have already studied this model in connection with the Burger's equation. And then also Bakhtin, Kator, and Khanin, they had additional works. But these were all d equal 1 and mostly n equal 1 as well. There is a related literature on Brownian polymers in random environment. Again, it's d equal 1, so not surfaces. And there are works of Benarus, Bourgade, and McKenna, following Fyodorov and Ledusal, that consider a fixed dimension, like a surface, but they take the codimension to infinity and they study something else, landscape complexity. So for the questions that we are studying, we are the first to consider this model in 2 dimensions, or 3 or higher surface dimensions, in the math literature. In the physics literature, this model has a long history. Of course, in the physics literature, it's kind of in the continuum. It's not always exactly this model, but roughly this model, starting at least from Hughes and Henley from 85. So this is kind of their canonical model, I would say, for this kind of phenomena. But it's not received much attention in math. Okay, now, in order to proceed, I also need to tell you what is the disorder function, these purple functions here. What is the distribution? Here, the numbers on the edges are independent, IID. I want to make the purple functions IID, but I cannot, it's in the continuum. I take an approximation to IID. I take them to be a white noise regularized. Regularized white noise is a function, say, convolved with some smooth bump. That's a nice function, which is kind of IID-ish. I don't go into many details on that, but we see smoothed white noise. These are independent between different vertical lines, and there are convolution of white noise with the bump. Our results actually also work for general disorder, satisfying various assumptions, stationarity, independence, concentration. I don't go into that. It does allow the disorder strength to vary between vertices. It does allow for later periodic disorder, but I don't go into that. What are our results? Yeah, question? No.
Yeah, there is a question from the audience.
Yeah.
Andrei?
Okay, thank you. Thanks for the lecture. Questions us just about the configuration file. On one of the earlier slides, 1 or 2 back, you have written that it should be continuous, not integer valued. And in your paper, I think at the end, you have special discussion about integer valued models.
Yes.
Thanks.
Right. So this model, the lattice model, takes integer values. This model, as I defined it, takes real values. But you could take this model and just restrict it to integer values. It is possible. It will be slightly different. The phenomena might be different. I might talk about that if I have time, or you can ask me at the end. But for now, I focus on the case it takes values in R or Rn. Okay?
Thanks.
We do think that this model models the same phenomena as that, but you sometimes need to be a little careful. You can ask me about the differences at the end if you like. Okay, so we go on to discuss results. As before, the main focus is first on how flat the surface is. I put 0 boundary conditions. How flat is it? How close to a flat plane? We already saw this question before. I'll go a bit quickly on this slide. I'll mostly focus on a table. Here is a table for n equal 1, for codimension 1. In the middle, I've put the predictions. The physicists tell us, as discussed in the beginning, that a first passage percolation model in 2 dimensions should fluctuate like L to the 2/3. In the previous model, we could only get L to the 1/3 as a lower bound and no upper bound. For this model, we can do much better. We can get L to the 0.6 as a lower bound, L to the 0.75 as an upper bound. The upper bound was known in the work of Yuri Bakhtin, but the lower bound was not for point-to-point fluctuations. But we go further. We study minimal surfaces. The physicists predict that the surface fluctuates with a certain exponent, 0.41, 0.22. These are obtained both via numerical simulations and via the functional renormalization group technique. We're able to get close. We get power law lower bounds and upper bounds, which are close to the predicted value in all of these dimensions. 4 dimensions is the critical dimension. It should fluctuate like log to a power. We do show it fluctuates, but we cannot get exactly a log, but we get close. And in 5 and higher dimensions, such surfaces are localized. These are this is a summary of the results. There is more results for if the codimension is not 1. I mentioned just one result that for a path, minimal path, in any codimension, we can show it's at least diffusive, which was not known for the other models. We cannot at this point solve the super diffusivity question for higher codimensions. This is one set of results. This is about localization and delocalization. Another set of results is about the scaling relation. We have the height fluctuation exponent, and we may also define a notion of the ground energy fluctuation, the standard deviation, say, or in fact, it should be something a bit different, of this minimal energy, of this quantity that we're trying to minimize, this one, the fluctuations of it, say around the median. That should also have an associated exponent. We call that that other exponent, we call that chi. And we discussed a scaling relation. Previously, we said that chi is 2 psi minus 1, but that was for minimal paths. It is proposed, say by Usen-Henley in 85, that there is a relationship for any minimal surface, but it involves the dimension d. If you have a path, you have -1. If you have a minimal surface of dimension 2, they're just equal, chi equal to psi, and so on. We're able in our model to rigorously verify this scaling relation, at least versions of it. I go a bit quickly for lack of time, but one thing is the version that chi is greater than 2 psi. So we ask, what is the deviation of the minimal energy from its median? What is the average height of the surface? If you have some chance for the average height to exceed h, then you have some chance for the energy fluctuations to exceed h squared L to the d minus 2. If h is your typical fluctuation, L to the psi, then your energy fluctuation would be L to the 2 psi plus d minus 2. So it is a verification of this direction in one for a notion of height and energy fluctuations. We also have an opposite inequality. If you're unlikely to fluctuate high, this time in the sense of the maximum, then you're also unlikely for the energy to make a large deviation in a somewhat different sense that we think is important, is essential, but I don't think I have the time to go into. We don't measure the deviations from median. We measure the deviations after resampling the disorder in half of the domain, in a concentric half. But I don't think I have the time to explain that in detail. But the idea is that this is the opposite inequality. And in dimension 1, we can do even better than all that. We can get some more precise bounds. This is all of our results that I'd like to present on this model, localization and scaling relation. And I want to say one word about the tool that allows all of that. The tool is the so-called main identity. We have this Hamiltonian, and the main identity discusses the following. Consider the surface that minimizes the Hamiltonian. I plot it in red for given boundary conditions. Now, take a certain a shift, we call it. Take another function, say this function. Move the minimal surface by adding the two functions together. Add the red to the green. So it looks something like that. What is the energy of the shifted function, h of phi plus s, versus the energy of the old function? But you measure the energy of phi plus s in a new disorder, in a shifted disorder. What is the difference of energies? We have an exact formula. Exact formula for this difference of energies. I'm
sorry, we're looking for a lead.
somewhere. Okay, I'm in a talk. I cannot help now. Okay. So in the shifted disorder, what is the difference of energies? Well, there is a very short calculation that just cancels the disorder and uses the fact that we have a quadratic energy, so it's an inner product, and a discrete Green's identity, but just 3 lines that gives us this result, which tells us that all that matters is the value of phi at the points where the shift function has a non-zero Laplacian, so in this case, the corners, and the energy, it's a Dirichlet energy of the shift function, of the green function. It's all that matters. And this gives a lot of consequences. I don't have time to explain them, but we understand exactly the effect of boundary conditions. We know if you put boundary conditions, then the surface is simply the surface with 0 boundary conditions shifted. If whatever boundary condition you put, it just shifts the surface in distribution and its energy also in distribution. In particular, in one dimension, it gives us a quadratic limit shape, the exact limit shape. In any dimension it gives, but the notion of limit shape is less clear in higher dimensions. It's even stronger than limit shape. So something we want to know for first passage percolation, we have for free here. It extends something called the shear invariance to harmonic invariance that we find. Okay, how much time do I have? 0?
I would say 4 minutes. We can go up to 55 without problem.
4 minutes, you say?
Yeah.
Okay.
5.
Okay, great. So I've told you about the main identity, and I've explained some consequence of it. I won't go into details, but one can also explain some intuition for the scaling relation stemming from the fact that if your surface wants to go to this height, because we know the effect of boundary conditions, we know it's going to pay h squared L to the d minus 1. This is the Dirichlet energy, of the harmonic extension of the boundary conditions. But in any case, we know how much it needs to pay to go to this height, and this should be somehow compensated by the disorder on this height, which should be L to the chi. This is the motivation why the scaling relation holds. It's not a proof. And I think Barbara will say more about actual proofs here. So this is an intuition. In the last 2 minutes, I say that there are other models that we wish to study. In these models, the disorder function, the disorder that we took previously to be IID, in these models is not IID. It is, for instance, a two-sided Brownian motion on every vertical line. This would correspond to domain walls of random field Ising model. Without going into that, I say that we have a second work where we study other disorders. Instead of white noise convolution bump, we study Brownian motions, even more generally, fractional Brownian disorder with Hurst parameter h. These look more complicated, But in fact, they're somewhat simpler also. We're able to confirm physicists' predictions, finding the precise fluctuation exponents in this case. In these cases, there are actually two scaling relations. They determine the fluctuation exponents, and we're able to prove that. This is in a more recent work. Again, we find delocalization with power law heights for surfaces of dimensions 1, 2, 3, delocalization but sub-power law height in dimension 4, localization in higher dimensions. But now we have the exact fluctuation exponent for any value of the Hurst parameter. In particular, you want Brownian motion, you just plug in h equal a half, and it does not depend on the codimension n anymore. So it's a different disorder, same model. It models a different physical phenomena, for instance, domain walls of random field Ising, and we can say much more. And we confirm physicists' predictions. There's even more disorders we would like to study. Periodic disorders, linear disorders is solvable, but the integer valued is not. This relates to random field XY. I don't have time to go into that. And here I just presented a selected list of open questions. For instance, prove the super diffusivity or lack thereof of minimal pads in high dimensions, find the exact delocalization of periodic disorder. There are fascinating predictions. Prove the roughening transition I mentioned in the beginning of the talk. Even for linear disorder, we don't know it. Show something about the distribution of the tails or the unimodality of the distribution of the minimal energy, for instance, or height fluctuation. Thank you very much.
Thank you very much, Ron, for this very nice talk. Let's open for questions from the audience. Any question? If not, maybe let me ask. So there are questions. Yeah, I just finished my question. It's very short. Like for this harmonic case, so is it interesting, or do you have some partial understanding of what could be the anharmonic case? Like,
what is the question? Harmonic case. What do you want to know?
like, do you have a similar model and some predictions for the anharmonic case?
I see.
Like,
so anharmonic could mean, perhaps that's what you mean, that instead of being quadratic cost
you have
to change,
potential.
it's some other cost. So you take this model, same model, but instead of paying quadratically, you pay, I don't know, the fourth power or the first power. We believe that these models behave the same. More essential is the issue that you take real values rather than integer. We don't think that the exact penalty, at least if it's convex, say, would make a difference. But our methods break down. The main identity used the quadratic nature. There has been an interesting result of Yuri Bakhtin and co-author on the differentiability of the limit shape for certain other penalties, not exactly the limit shape still. So there are some results, but nothing as encompassing as what we have for the quadratic, and all of it is due to an exact identity that holds in the quadratic case mentioned here, and uses that the quadratic can be written as a product like that, as a bilinear function.
I see. Thank you. So there was a question from the audience. Please. No more? Okay. If there is no other question, okay. Let's thank Ron again for the nice talk. I guess you have to run to teach.
I'm teaching in 1 hour. I might need to run at the end of the Barbara's talk.
At the end of the talk, okay. Sounds good. So I would say that, okay, we can close. For now, we take 5 minutes break and we resume at past 5. So whatever time is in your time zone. Okay?
Thank you.
See you soon.
See you.
So we can start. I can just for the recording, I can say that okay, we now resume with the second talk with Barbara Dembin from Strasbourg and on minimal surfaces in a random environment, part 2. And please, Barbara.
So thanks a lot for the invitation. So in my talk, I will really focus on the last model Ron presented, that is a harmonic minimal surface. So I will recall the model and focus more on the proofs to give the main statement and give proof ideas so that I hope to convey why this model is more amenable to analysis. Okay, so let me start to recall the model so that we are all on the same page. So for us, a surface is going to be a height function, and to each point of ZD we assign a height, so it can be in Rn. And we have the disorder, so the disorder is living on ZD times Rn, and to each point in ZD times Rn we associate a value. And so if we look on the picture, so the surface is so the picture is for dimension 1 and n equal 1, and to each point of z, to define a surface, you have to assign a value that are my yellow points. And then the energy of a surface, so you count this contribution correspond to the elastic energy, so you count for two consecutive integral value what's the square of the height difference between two consecutive points, plus you count all the noise contribution that your surface sees. So at each point where your surface is, there is a noise value, and you sum all these values. So as Ron explains, this energy is the sum of two terms wanting different things when you want to minimize. Because if you want to minimize and you don't have the noise contribution, what you will want to minimize the elastic energy is to have a flat surface. But you have the second term where you want to pick the best noise as possible, that forces you to fluctuate to go pick the best noise as possible. So our energy is really a sum of two contributions wanting a different thing. So one wants to be as flat as possible, and the other one wants to fluctuate to go pick the best noise. And somehow, when you minimize, there is a competition between these two things you want to do. And so when you minimize surface, it's important to have an anchoring. Just as when you were looking at minimal path, you were looking at paths between 2 points. So this is an anchoring to say between this and this. And you need the same in surface, because if you just look at minimal surface without any anchoring, it could go to infinity, go pick a very pathological noise. So for us, the way to define our anchoring, we will study on a lambda that are subset of ZD, and the way we will anchor is by saying that the surface has to be equal to 0 outside lambda. So it's like you were anchoring like around a boundary of a square. And we denote phi, eta, lambda, the corresponding minimizer if they exist. So so for the talk, I will not care about the strength disorder. I will just leave it to 1 everywhere, but in all our results, we have explicit values on the dependence of lambda. Okay. And so so maybe I will go spend more time on the assumptions. So we have a very general assumption on eta, but we also work with specific noise. So Ron mentioned the white noise, the version of eta that is a white noise, and for this noise corresponds to you have if you have in dimension 1, you have a white noise on each copy. Oops. Yes, shouldn't. You have a white noise on each copy of Z, an independent white noise, and to assign the value at a given point, you integrate the white noise against a compactly supported bump function. And so that you get a noise that is independent and kind of mimic what you would have, what you have in first passage percolation. So this is like white noise. But more generally, we work with noise with these assumptions. So we need that the minimizer exists. An important assumption is stationarity. So as you've seen in the main identity run show, we will want to shift the environment. So you have the environment, and we sometimes want to shift it to move all the environment according to some shift function. And we want to make sure that when we do this procedure of moving the environment, it still has the same distribution as the original noise. So this is for stationarity. And we also want like independence. So we have both independence. If you look at two copy, if you look at V and U with V different from U, they will be totally independent. And otherwise, if you are like at the same V, if you take 2 points on the line that are like a distance larger than 2, they are independent. That's our assumption. And finally, we have a concentration assumption. And so if you are familiar with like Efronstein inequality, like a surface is typically something that uses a volume of order the size of lambda. And if you're familiar with Efronstein inequality, this tells you that the variance is smaller than the square root. That the variance is smaller than the volume of lambda. And this is more kind of a Talagrand concentration inequality. That's like the improved version of Efronstein, where you have also tail associated to this square root of this standard deviation of square root of lambda. So this is something quite natural to expect when you have a random variable depending roughly on a volume lambda, to have this kind of concentration estimate. Okay, and so this is the main identity that is really like at the core of all our proofs. So we are using it all the time, and that enable you to compare the energy of a surface with the energy of the shifted surface, where the environment is also shifted. And this is really useful to compute what we call like cost to go up. Like we can force the surface to go up, and we can control the cost it has to force the surface to go up by shifting it by a function. And okay, so now I will start with the proof and start with the part on localization and this side of the scaling relation. So we have a concentration lemma, and in fact, like here, you can replace this by any value. So it can be any gamma. So in particular, it's also true with the median. That's the version Ron presented. And so what is this lemma is saying? So S can be any function. So this thing is an observable, and it can be any linear observable of phi eta, because S can be anything. And it controls the probability that this observable is large by the probability that G minus its expectation or G minus its median is large. And the good thing is that the right-hand side is something you know very well how to control with our concentration assumption. So we bound the probability that some observable is very large by the probability that you are far from that your energy is far from your expectation. Okay, so just for this thing to be less obscure and to understand why it is useful, let's look at two applications of this concentration lemma before proving it. So example 1. So for instance, we can choose S. So again, we can choose S anything we want. So we can choose S such that the Laplacian of S is equal to the indicator of V, where V is in lambda. And if you choose S that way, then you have a control of phi eta lambda. So this linear product is just phi at V. So recall that phi eta lambda is my minimizer. Is the minimizer of the energy when you restrict to lambda. Okay, so here it's a very simple example. You choose S like that, then you can, it means that when you choose S like that, you can have a control on phi V eta lambda larger than R. Okay, so it seems great to be able to control like to have an upper bound on how large the height value is. So we can try to see what's the value of S in the case of dimension 1. So in the case of dimension 1, how do you want to choose S such that this is equal to that? So if you have minus L, L, let's consider, to simplify, V equals 0. So the correct function to choose is this function that is equal to L over 2, so if I'm not wrong. And if you compute the Laplacian minus the Laplacian, you will get that it's equal to 0 everywhere except at this point where it's equal to 2 minus 1. And so when you have this function, now to be able to apply this concentration lemma, you need to estimate this quantity. And this you can rewrite as S scalar product Laplacian of S. This is just like a Gauss-Green identity, discrete Gauss-Green identity, because you can rewrite as, and this is an inequality. And not this thing, so the only term that is not 0 here is this one, so you will have L over, so this scalar product is going to be equal to L over 2 times 1, so L over 2. And now if you replace in here, so you know that, so you have R square, so this is equal to R square over L. And when is this thing starting to be large in the point of view of G minus expectation of G, is when it's larger than square root L, of the order square root L. This is from the concentration estimate, because we know that we have good concentration estimate above square root L. That is when this energy difference is larger than square root L, we know that we will decay, if it's larger than T times square root L, it will decay like E minus T squared. And when, so what does it give for R? It gives R larger than L 3/4. So as I say, with the concentration, this says that phi 0 eta lambda L is smaller than constant L 3/4 with high probability. Just because you can control that the probability, when the constant here is large, the probability that when you replace S by that, the probability that it's larger than L 3/4, you will start to seeing a decay. It will start to decay when it's above this thing. Yes. So this gives you an upper bound on V. And so this is the upper bound Ron presented in his table. But this is not the right way. You can think, okay, now I can do the same in dimension 2 and higher, but it will not work well. So you have in dimension 2 you will have a log loss compared to the result Ron presented, and it doesn't give totally the right result in a higher dimension, because you need to do some multi-scale analysis instead of directly using one S. You will need to use several S and to compare with using geodic scale to the increase over geodic scale. So it's a bit more involved in higher dimension, but just in dimension 1, it just gives you a hint why this concentration lemma is useful. And so another example is related to like the scaling relation. So now we want to choose S such that this time we want to see the average. So to see the average, we want to have that the Laplace minus the Laplacian equal to 1 over lambda L indicator of lambda L. So that when you have such an S, when you replace, the observable you see is the average of phi eta over R. In that case, it's like phi. In that case, it's equal to 1 over lambda L so it's equal to the average. So when you have such a S, you control the average of phi over lambda. And so now it's so if you want to, it's the same game now. If you want to have a control, you need to estimate the Dirichlet energy of S. So what's the value of S? So how can you choose such a S? So if you are a bit familiar with random walk, you can choose S as 1 over lambda L, expectation of X to lambda L, where this is the exit time of a simple random walk starting at X when it exits lambda L. And so you can check that if S is chosen like that, normally the Laplacian is indeed equal to that. And so you can bound Sx by, so so for X in lambda L, what's the maximal time you spend in a box of size lambda L? You have the uniform bound of L square. So you have L square over lambda L. Because that's the typical order of the maximal time you spend in a box of size lambda L when you start anywhere in the box. Of course, the estimate is better when you start close to the boundary, but this is sufficient for it. And so that we have, when you compute S minus, okay, maybe I will take a new page. So, okay. So that you have if you compute that, oops. So it's equal to lambda L times L2 over lambda L times 1 over lambda L. And at the end, it's equal to L2 minus D. Okay, because SV is smaller than this, and this is delta, the Laplacian S at V is smaller than this, and lambda L correspond to all the V. So this is a bond. And now, when we replace, we have probability that the average of phi larger than R is smaller than 3 times the probability that GE eta lambda minus, we could replace by the median, is larger than R square LD minus 2. Okay, just so that I show you back. Yes, this was divided by this, so you get with a constant, with some constant. Okay. And so this is this version of the scaling relation, this direction, sorry. So how can you understand it that way? So Yeah, the thing is that we expect that the like GE behaves like L chi, and that the typical height behaves like L to the xi, but it's hard to give a rigorous meaning to these exponents, right? And these relations are more contains more information than just that, but can be understood in this way. So why? So let's say this has a meaning. Then it means that you could expect that the probability that the average of phi being larger than Lxi to be of order to be at least larger than a constant. So it's a bit a big assumption, because you say if the typical height is L to the xi, then the average is L to the xi. So it's not very clear, but this is just to understand where it comes from, the scaling relation. So if you have this, then you have that the 3 times the probability of G is larger than L to xi plus D minus 2. So what you're saying is that the chi, since this is the probability that G deviates from its median by this is something typical, because you have a constant probability of having this means that chi has to be larger than 2 xi plus D minus 2. Okay? So because this says that if this is typical, so if you have a typical average fluctuation, then it gives you a lower bound on the typical energy fluctuation. So this is why you can understand this this inequality as this version of the scaling relation. Okay, so now we can prove this lemma. And again, to prove this lemma, we need to use the main identity. Okay. So in this, it's just a use of the main identity for phi and the shift rho s. So here, s can be any shift function. So s. Okay. And now, if you choose rho that way, you have that if this thing. So if now if you replace, you have minus r square, and here you have minus r square square. And so if this is over 2, so if this is larger than r, then it means that this thing has to be smaller than minus r square divided by 2. No. So this is just from this. And so here we have applied with phi eta being the minimizer of h eta. So this thing by definition it's equal to g eta. And then for this inclusion you use that since this is not the minimizer, it has to be smaller than ge eta rho s. So in particular, since it's smaller, you do have the containment that way. Okay, and so what you have is that you have two ground energy and GE eta, and they are both like far from each other. And the important point is that since you have stationarity, these two ground energy, they have the same distribution. So they have the same distribution. And so what you say is that if they are far apart from each other, there must be one that is far from the expectation. And that's so either it's either this one or this one. And then you do the same argument for minus r, and at the end so what you have is that if this observable is large, it means that someone has to be far from the expectation. And here you see in this proof that I use expectation, but it can be any value. The proof is still true with any value gamma if you replace the expectation by any value gamma. Because if you have that the two values are far apart, then one of them has to be far from a given gamma. So that's why you can use expectation or median or whatever. Okay. But again, main identity to prove the lemma. So now I will speak about like the over. So we have really two sides. We have the localization and the over sides of the scaling relation, and the delocalization on this side of the scaling relation come together. And so what we prove is our main proposition is the following. And so this eta lambda bracket lambda L over 2 correspond to the noise where you resample in the bulk. Okay, so you have your lambda and you choose to resample here. Lambda L over 2, you resample the noise. And you want to understand the fluctuations arising from the bulk. So what's the difference in ground energy you obtain by resampling the bulk? So this term can be really understood as like fluctuations arising from the bulk. So a priori, it's not clear that they do correspond to the real fluctuation. That is, maybe the fluctuations arising from the bulk are of smaller order than the real fluctuations. But again, this proposition may be interpreted as this side of the scaling relation, where here chi, where you kind of make the assumption that the fluctuation arising from the bulk are of the same order as the real fluctuation. So because what you want to say is that let's say h square LD minus 2 is of the order L to the chi. Okay. So if this is of order L to the chi, what you have is that you expect that the probability here to be something typical, so to be at least constant. So you expect that the probability that the max to be larger than some constant. So what this says is it says that psi L to psi LD minus 2 has to be larger than L to chi. Since when you choose H, it's a typical fluctuation for your surface, it means that L to the psi, that is the typical fluctuation, the maximal fluctuation for the surface, has to be greater than this H. And when you have this, you get like this over side of the scaling relation. Okay. But so this proposition really captures what Ron was explaining. Like, if you have too much energy, somehow you have to delocalize, because this is what we will see in the proof, is that you have somehow a cost to go at distance h, and if h is small, the energy you gain by seeing a new environment is going to be larger than the cost you have to pay. So typical surface will indeed go up to height h, because the cost to go up to height h is going to be compensated by the gain you have by seeing this new environment. And so this will be more transparent in the proof of this proposition. But yes, before going to the proof of that, just let me explain how from this inequality we deduce some delocalization. So if you want to deduce some delocalization, you want to be able to find H such that the probability on the left side is typical. So you want to have a way to lower bound the bulk fluctuation. And so for the case of white noise, we do have, and our result of delocalization are valid only for white noise. And somehow the idea is that let's consider like a surface that stays like most of its time in a cube of width h. So your surface. Okay. So what's the when you are in a white noise, so if you want to simplify, you can think of a discrete thing where you can think of the first passage percolation model. It's good enough for intuition. So you have natural fluctuation of the average of the energy, of the average of the noise in this box. Just you look at the average of the noise, you sum all the noise, you divide by the volume of this box, you have natural fluctuation that are like Gaussian. So typically, the variance for the average of the noise, it behaves like when you renormalize, it behaves like square root. So it's not the average, it's the standard deviation. So variance is without. Okay, and since you can hope that typically each point of your surface will have naturally this variance, and that it's like something like independent. They vary independently like that. And so what you hope is that the total contribution of this thing, since you have a volume lambda L of points, you will have lambda L times so it's L. So these are with the white noise. When you choose the noise to be the white noise, this is somehow an easy lower bound we get on the fluctuation without understanding anything of the surface. Like the only thing we use on the surface is that it spends most of its time like inside this box. And just by like natural variance of the environment, this is the lower bound you get. So it's really some weak bond that we can get. And so when you have that h square, if you choose h square ld minus 2 to be of this order. So yes, by the way, here I work with n equal 1 when I say that. When you choose h like that, normally you obtain h equal, and this corresponds to the lower bound we obtained for the surface. So because when you choose h like that, you can prove that the probability of this thing is something lower bounded by something constant. So it's something typical that you see with a positive probability. So it implies that with positive probability, your surface go above this height h. And so this is why it's a delocalization result, because it gives you a lower bound on typical fluctuation of the surface, on the maximal value of your surface. And so we actually have better, but it's, the result to obtain it is the proof to obtain it are a bit harder, because here it will correspond to the proof of having one point being at a very high value, but it's always possible to have like isolated points that are at this very large value. So a more interesting result is to be able to say that there are positive fraction of points of the surface that go above these values. And this is a result that we were able to get, but just the proofs are a bit more complicated to explain. So this lower bound, we are having it not for one point, but for like positive fraction of the point, we are able to prove that there is a positive fraction of the point that go above this height. Okay, so now I can kind of give an idea of the proof of this proposition. And so normally it should illustrate like this the fact that if the energy cost is smaller than the energy gain, then you will delocalize to this height h. Okay, so let's prove the result. So I denote zeta the noise eta where you resample in the bulk lambda L over 2. And I denote A and B two events. So A and yes, and this H, so it's kind of having this H here in the subscript mean that it's a ground energy where the surface is restricted to have absolute value less than H. Okay. And when you have this notation eta S, that's the shifted environment. And here we will choose a shift function S in such a way like you want to push your surface to go to height h. So in the bulk, so in lambda L over 2, the shift function will be of will have value larger than 3h. Okay, so we will want to so we can choose it in such a way that like the corresponding cost is of order h square LD minus 2. So it's not complicated to find such a function and to compute that, but I will not explain how we do that. But so you can use a shift function such that you have a good control on the Dirichlet on the Dirichlet energy of this function, and this function will really push your surface to have a height h. Okay, so now what happened on the event A intersected with B? So, okay, so why did I put my thing like that? So I have additional inequality. So I have two inequality that comes from the main identity. So the first one, so it's I don't detail how to obtain them, but it's really a small computation just using the main identity. Okay, so but these are just using main identity, so you have to apply the main identity to the right noise and the right surface and the right environment, but it's not too complicated to get. And these terms here, you can really it's really related to this, and you can interpret that as like the energy cost to move your surface to height h. Okay. So now let's say in my picture, and we will see that there is a problem in my picture if I do that. Let's say that GE eta is equal to G eta H. That is, so this means that the unconstrained noise, the unconstrained energy is equal to the constrained energy. So for the surface realizing the minimum for GE eta is actually a surface that has value at most h. So we will see that we cannot be on this event, on this intersection of events. So I assume the same for g e zeta. Okay. So now, so we have so this thing, the fact that they are far apart, it comes from this, from the event A. The ordering like that, it comes from this. That sorry, I should change the over. Sorry. Okay. And now what do we have? We have that GE eta H. So you know that, so so the two here are equal. So you know that this one, okay, so it's not clear that this one is on its right, but it cannot be no, yeah, sorry, it's clear that this one is on the, no, it's not. So the two here, they should not be too far from each other. And same, it's the same for the, okay, maybe okay, I think I did my picture wrong, but okay, it should be the opposite. But somehow okay, never mind. The idea is that, but I think I choose my thing wrong. Like the idea is that this thing is going to be too large, but it is forced to be large, but the over cost has forced to be close, and you want to be on so I choose my events badly, but you want to be on an intersection of event that is empty. So meaning that it's not possible to have these four events at the same time. Okay, let's say let's say I did not make a mistake here, and that we have that this is empty. Just to conclude the proof. And then it's just a matter of choosing well the thing. Okay, so let's say this is empty. So it says that A intersection of B has to be contained in either this one delocalize. So either you delocalize for the when you have the noise eta, or you delocalize for the noise. Because somehow the event A tells you that you have a big gain in energy, and since the cost to go up it will be of smaller order than this gain of energy, there has to be somewhere a surface that delocalize. That's the idea. Okay, so you have this very well, and then you want to compute the lower bound on the probability of A intersecting with B. And so, and for that, you will need to condition on the noise outside lambda L over 2 so that they become independent. Because if I condition on the noise here, then since it's the shifted environment and the shift is low, they are both function of different portion of space, in the disjoint portion of space, so they are independent once you condition on the noise outside, because this thing, since it's constrained on h, looks at the things that are below height h, but here, since it's shifted, it looks at things that are like not at the same region of space. So once you condition outside, you have that it's independent, so probability. So you have that it's independent. Okay, and B is something totally symmetric, so it's at least 1/2. So because there is no one that since you have resampled in the middle, there is as much chance that one is larger than the other. And so at the end, you get that it's larger than 1/2 probability of A. And this is larger than 1/2 probability of the same thing without the H. Intersected with G eta. Okay. And now if you put this together with this, at the end you obtain normally, because you obtain probability of this event smaller than so it's 6 times the probability of not being okay. And here we use that G eta and G zeta has the same distribution because of the stationary assumption. Okay, so yeah, so it's just computations. It's the main point is really like you have this trade-off of energy gain and energy cost, and once the energy gain is overpassing the energy cost, then you have too much energy to stay within your thing of height h. You will just exit with high probability. Okay, but just to give you like a hint of what this kind of proof look like. Okay, and just to conclude, let me just say a word on the noise, the new work with a new noise. So now we have eta vt is now a fractional Brownian motion. And this is the covariance property. So in particular, if you take h equal 1/2, you have just two-directional Brownian motion. And so what's the main difference is that the noise is no longer stationary. So when you do shift, when you shift the environment, it has not the same distribution, and you have to make a correction to just like for Brownian motion. If you shift the Brownian motion, you have to make a correction such that it's again the same distribution. So here you need to do the same when you define the shifted version. You have to correct so that it has the same distribution. So we have a new version of the main identity where we have a new term coming from the fact that it's not stationary, but we are still able to prove the scaling relation. And the special thing of this model is that we have a new scaling relation, this one. And this scaling relation plus this scaling relation is enough to get the exponent. So we, at the difference of our previous work with general noise, we were only able to get lower bound and upper bound on the exponents. Here we really are able to compute the exponents for the fluctuation and the fluctuation in energy and the fluctuation in space. And so maybe just to give you an idea on where this comes from. So if you have a surface, and Lxi is the like the height, the typical height. So what you have is that the variance of a point value at height Lxi is of the order L to xi h. So this is just a computation of the variance using this thing. And typically your surface, when it's of typical order LXI, will have like most of this point at this height. So the variance of the surface is going to be at least, and also upper bounded by LD, so the number of points, times this L2CH. So this is where you get, so you get 2K equal D plus 2 psi H. Because really, like if you think of Brownian motion, the higher you are, the larger variance you have. So it's not no longer as a IID noise where wherever you are, you add the same variance. Here it's the higher you are, the higher is your variance. And since typically when your typical height is LXI, you have all your points at height LXI, and a given point, the noise at height LXI has this variance. When you sum all the variance over all the points of the surface, this is what you obtain. Okay, so thanks to this new scaling relation, we are able to have all the exponents. So I'll stop here. Thanks.
Thank you, Barbara. Thank you a lot for the very nice talk. Thank you for entering also into details. I think it was gave a lot of intuition of what's going on. Thank you. Again, do we have questions from the audience? Yes.
Thanks. It was very interesting. So minimal surfaces are very frequently linked to complex analysis. In which places in your analysis do you include this element? Thanks. Just out of interest. If anywhere, but just.
Yeah, I don't. From my point of view, we don't. But maybe Ron, you have a different.
Okay.
Well, we do estimate Green's functions.
Yes.
It appears that the height fluctuations are tied to Green's function estimates for a random walk. So it's a bit related perhaps to analysis, but we're not using specifically anything two-dimensional. So the dimension of the surface and the codimension could be arbitrary. So it's not really about complex analysis, I would say, but Green's function estimates enter.
Of course. Good. Thanks.
Nice. Any other question? Okay, I think there is no further question, and also from my side, it was very nice. And yeah, I think we can close here. And thank both of you for giving these nice lectures. And yeah, we resume in 2 weeks. In 2 weeks from now with the next.
Thank you very much.
Thanks for having me.
Thank you.
Bye.
Thank you. Ciao.